Okay, welcome to this deep dive.
Hello.
Today we're plunging into, well, a whole stack of sources, articles, some research notes, personal reflections that map out a really fascinating journey.
Yeah, it's Alex's story, his um, odyssey, you could say, going from seeing data as just, static numbers
Right, boring spreadsheets.
to really discovering its incredible power, how dynamic it is.
That's right. And our mission here with this deep dive is to take Alex's whole experience, unpack all this material, and pull out the most crucial insights.
We want to give you a kind of clear roadmap, yeah, a shortcut maybe to understanding what data actually is.
And how you can start to analyze it and maybe where the cutting edge of data science is actually going.
Think of this as your guide for navigating this increasingly data-driven world, finding those aha moments.
But without getting totally overwhelmed or lost in the technical jargon.
Exactly. So let's dig in.
Okay, so Chapter 1 in Alex's journey, it's really about this awakening moment.
Yeah, the point where he starts to see that the world itself is like fundamentally made of data.
It kicks off with just redefining data itself. It's not just those spreadsheets we mentioned.
No, the sources describe it as the raw, unorganized facts, observations, figures. They're literally everywhere.
Like the temperature outside right now,
Yeah.
or the words in an article you're reading.
Or the stuff in your online shopping cart, every single click you make online. They call it the unseen fabric of everything.
That's a great way to put it. And Alex quickly learned this fabric. It has different textures, different types.
Absolutely.
Uh-huh.
First, you've got quantitative data, things you can count or measure, numbers.
Like number of products sold, or someone's height.
Exactly. Measurable things. And then the flip side is qualitative data, sometimes called categorical.
Descriptive stuff.
Quality. Right. The color of car, maybe the actual text in a customer review, different species of plants. It doesn't measure numerically.
And the sources also talk about how this data fabric, well, how it's structured, or more often, how it isn't.
Yeah, that's a big one. Structured data is the neat, tidy stuff. Think data perfectly organized in tables, rows and columns,
Like a traditional database, fits in nice boxes.
pretty much. Then there's semi-structured. It's got some organization, maybe tags or markers, but it's way more flexible than a rigid table.
Like JSON files, maybe?
JSON's a great example. And then the big one, the real challenge often, is unstructured data.
Images, audio, video.
Free-flowing text documents, just stuff that doesn't fit into any predefined structure easily. The Wild West, you called it.
Yeah. And this is where Alex apparently had one of his first big aha moments. A really critical concept from the sources. Data types.
Sounds technical, but it's so fundamental. It's basically a label, a human decision. We give a piece of data.
To tell the computer exactly how to interpret it. Right?
Precisely. Because without that label, that human structure, the computer has no idea if 50 point is $50 or 50 years old or 50 miles an hour.
And if you get that wrong.
Everything downstream breaks. The sources are really clear. Misunderstanding or misapplying data types makes the whole analysis unstable, prone to errors.
For Alex, it was sparked by some work challenge, apparently. Just this massive information he couldn't make sense of.
And the light bulb moment was, okay, data is everywhere, but defining it correctly, giving it the right type, that's the absolute key to unlocking what it means.
So let's drill down on those building blocks then. The common data types Alex had to wrap his head around. Why are they so important practically?
Well, they're like the foundation of a house, really. Get them right, and you ensure the data you collect and store is in the format you actually intended.
And the values are what you expect.
Exactly. Try doing math on text, or storing a date in a number field. You just get errors. Or worse, you lose information silently. It breaks everything.
Okay, so based on the sources, what are some common types he ran into?
Well, the basic number ones first. Integer. Int, that's for whole numbers. No decimals.
Things you count, like customers in a store, products in stock.
Perfect, like 7 or Negus' 707. Then floating point, float, is for numbers with decimals.
Measurements, money, weights.
Yep. $19.99, $707.07, 0.5 kilos. Then string, stray or text, that's for sequences of characters.
Names, descriptions, addresses, hello world.
Exactly. And importantly, things that look like numbers, but you'd never do math on, like phone numbers. You store those as strings usually.
Good distinction. What else?
Boolean. Bool.
Yeah.
Super simple. Just true or false. Often stored as 1 or a 0.
Binary states, right. Is the customer subscribed? Is the feature turned on?
Precisely. Datetime types are obvious specific points in time. Transaction dates, timestamps. 2023, 10, 27, or maybe down to the second.
Okay.
An array or list, that's an ordered collection of items, usually similar types.
Like the items in your online shopping cart, milk, bread, eggs.
Exactly like that. And one more the sources mention is the enumerated type, enum. This is handy when you have a small, fixed list of possible values.
What's like product condition, new, used, refurbished, or maybe priority, low, medium, high.
Perfect. Those are enums. Understanding these wasn't just academic for Alex. The sources use a grocery bill example, strings for item names, floats for prices, integers for quantity. Getting that structure right from the start is the bedrock.
But, as Alex quickly found out, real-world data, it's rarely that neat and tidy.
Oh, tell me about it. It's messy. Which brings us straight to the next big quest. Why data quality matters so much.
So you can have the type defined correctly, but the actual data point could still be wrong or missing.
Exactly. Data quality is all about how fit a data set is for its intended purpose. Is it good enough to use?
And the sources break down quality into different dimensions, right?
They do. Accuracy is the big one. Does the data reflect reality? Is that email address actually correct? Is the sales number right?
Okay, makes sense.
Then completeness. Is all the data you need actually there? Or are there lots of missing phone numbers in your customer list?
Yeah, gaps are a problem.
Consistency is huge too.
Yeah.
Is the state always listed as California or sometimes CA or maybe even Calif? Are dates always in the same format?
Oh, that sounds incredibly frustrating to deal with.
It is. Then there's timeliness. Is the data recent enough for what you need? Last month's sales figures might be useless for planning this week's inventory.
Right. And validity.
Validity means it follows the rules. Like, a date of birth has to be a plausible date. A quantity ordered probably shouldn't be negative. It conforms to defined rules.
Got it. And uniqueness.
Just means no duplicates. You don't want 3 different records for the exact same customer.
The consequences of getting this wrong, the sources say they're pretty bad.
Dire is the word they use sometimes. Misinformed decisions, wasted money and time, maybe even failing to comply with regulations. Poor data quality fundamentally erodes trust.
That garbage in, garbage out phrase really hits home here.
It's not just a cliche, it's like the first law of data analysis. High-quality data isn't a given. It requires deliberate effort.
Which leads to data quality management, DQM. Cleaning, validating, monitoring.
Yeah, the whole process. Alex's initial frustration with messy data turned into this deep appreciation for DQM.
It's not the glamorous part, maybe, but it's the absolute foundation for any trustworthy analysis.
Okay, so with a handle on what data is, its types, and why quality is critical, Alex starts moving into Chapter 2, becoming a data analyst, finding those first clues.
Exactly. Moving beyond just cleaning data to actually extracting meaning from it. Uncovering the stories hidden inside.
So data analysis.
Yeah.
The sources define it as a systematic process.
Yeah, systematic, inspecting, cleansing, building on what we just talked about, transforming, and modeling data, all with the goal of finding useful info, drawing conclusions, helping make decisions.
At its heart, it's about asking questions.
And finding verifiable answers in the data you have.
And the mindset Alex needed to develop.
Curiosity is key. Also, a healthy dose of skepticism, don't just accept numbers at face value, attention to detail, obviously, and a methodical way of tackling problems. Right. And the sources show that analytics isn't monolithic. There are different types Alex learned about, starting with the ones looking backward.
Yeah, the retrospective types. First up is descriptive analytics. This is basically summarizing historical data. What happened?
Spotting patterns, trends, like a snapshot of the past.
Exactly. Like a retailer sees sales jumped last December. That's descriptive.
Or in Alex's coffee shop example from the sources. Finding the busiest day, the most popular drink, average spend.
Perfect examples. Just stating the facts of what occurred. Foundational stuff.
Then comes diagnostic analytics. This digs deeper.
This asks why something happened. You're looking for the root causes behind those trends or anomalies you saw in the descriptive part.
Like, why did coffee sales dip last Tuesday? Was it the weather? Some local event?
Or maybe the espresso machine was broken all morning. Or a competitor opened nearby. Diagnostic is about investigating the why.
And the sources say these two work together.
Like detectives. Descriptive spots the clue, the sales dip. Diagnostic investigates the cause.
Okay. Now, to actually do this analysis, Alex needed better tools than just spreadsheets, right? Chapter 2 introduces his starting toolkit.
Yeah, spreadsheets are great, but they hit limits fast with complex data. The absolute first indispensable tool is SQL, structured query language.
The gateway to structured data, they call it.
It really is. It's the standard language for talking to most relational databases, where tons of valuable data lives. It lets you pull exactly the data you need.
And the core operations, Alex learned. They seem simple but powerful.
Very. Select and from are the basics. What columns do you want? Select and from which table from. Like select product name, price from products.
Okay, then where for filtering?
Yep. Where lets you filter rows based on conditions. Show me orders where the order date was yesterday. Or products where price 20.
And group by why, that's for summarizing.
Exactly. You group rows together based on some category, like group by Y product category. And then you can use aggregate functions like count, SUM, AVG on each group.
So you could find total sales per category or average order amount.
Easily. Select OVG order amount from orders or count unique customers. Select count, distinct customer from customers.
And order by just sorts the results.
Yep. Order by price, DECI, shows highest price first. Simple, powerful building blocks.
Alex practiced using these to, as the sources say, uncover clues efficiently.
Pulling data, filtering, grouping, summarizing. It's the foundation of getting data out of databases.
But just staring at tables of numbers, not always the best way to see patterns or share insights.
Definitely not. Which leads directly to visualization tools like Power BI and Tableau.
Business intelligence tools for data storytelling.
That's the idea. They bridge that gap between complex data and human understanding. Let you paint pictures with data, make it intuitive.
Alex started with Power BI, it seems, importing data, making basic charts.
Yeah, import an Excel file, maybe, then build a bar chart to compare sales across regions or a line chart to see sales trends over time.
And the sources mention an aha moment here, seeing a pattern visually.
Exactly. Like seeing that sales dip on the line chart and realizing it lines up perfectly with the day a new marketing campaign launched. Something you might miss in the raw numbers.
Then Tableau, maybe focusing more on structured storytelling, building interactive dashboards.
Yeah, Tableau's great for that. Starting broad, letting users drill down, making the data not just informative, but also aesthetically appealing, engaging.
Okay, SQL for getting data, BI tools for visualizing, and then the next step felt bigger. Programming with Python and Pandas.
Python's this hugely versatile language, super popular in the data world, and Pandas is the library within Python that's the absolute workhorse for data manipulation and analysis.
The sources call it the de facto standard.
Pretty much. It's more flexible, more powerful, more scalable than just SQL or BI tools for complex data wrangling, cleaning, and preparation. It's the essential bridge to doing more advanced stuff.
So Alex learned the basics. Loading data.
Yep, loading data, often from a CSV file, into a Pandas data frame. You can think of a data frame like a spreadsheet or a SQL table, but right there in your code.
And ways to quickly explore it.
Key commands, like df.head to see the first few rows, df.tail for the last few. df.shape tells you rows and columns. df.describe gives quick statistics for number columns. And df.info is super useful, shows data types for each column, and counts non-null values. Great for spotting missing data early.
It sounds like you can do a lot with just a few lines of code.
It's surprisingly powerful, gives you programmatic control. This was just scratching the surface for Alex, but it opened up a whole new level of capability.
So Chapter 2 wraps up with Alex's first real triumph, putting these tools together.
Yeah, applying the skills, using SQL to get the data, maybe Python and Pandas for some heavier cleaning or feature creation, then Power BI or Tableau to visualize it all.
To solve a tangible problem, like figuring out why user engagement dropped or analyzing personal investment?
Exactly. Define the problem, get the data, clean and explore it, visualize the insights, and crucially present them.
And the reward was seeing those insights actually lead to a positive change.
That's the payoff. Rolling back a feature that wasn't working, shifting marketing spend, refining an investment strategy. It proves the value of the analysis.
And this success, it solidified his passion and made him look towards the horizon, towards data science.
Which brings us nicely to Chapter 3. Beyond the horizon, Alex starts exploring data science. The focus shifts.
From understanding what did happen
to predicting what will happen.
Yeah.
And maybe even influencing it.
So data science, how do the sources define that? It sounds broader than analysis.
It is broader. It's described as multidisciplinary, using scientific methods, processes, algorithms, systems, all aimed at extracting deeper knowledge and insights from data.
It sits at an intersection.
Yeah, intersection of statistics, computer science, and crucially, domain expertise, really understanding the subject area you are working in.
So the goal shifts. An analyst explains why sales dropped last week,
while a data scientist tries to build a model to predict if they'll drop next week, and maybe by how much. It's moving from reactive to proactive, building models that learn.
The sources draw a distinction between analyst and scientist roles. What are the key differences?
There's overlap, for sure, but generally, an analyst focuses more on past performance, answers specific business questions using descriptive and diagnostic analytics. They primarily work with structured data. Tools are SQL, Excel, BI, maybe basic Python.
Okay. And the scientist?
Goes deeper. Focuses on forecasting, building predictive models, sometimes even developing new algorithms or data products. They handle all kinds of data, structured, unstructured, semi-structured.
Skills are more advanced, too.
Definitely. More advanced Python, or R, a stronger grasp of statistics and probability, understanding machine learning algorithms, often cloud and big data tools. The math foundation calculus, linear algebra, becomes more important, and a big part of their job is actually building models and systems, automating things.
So it's more technical, predictive, maybe more research-focused.
That was the pivotal realization for Alex, yeah.
Yeah.
It required digging into more technical areas to build these predictive capabilities.
And the first big step into that predictive world is predictive analytics.
Exactly. Answering that question, what might happen next? Using historical data, stats, and machine learning to forecast outcomes or probabilities.
The possibilities sound really powerful. Predicting customer churn, forecasting product demand.
E-commerce recommendations based on your past behavior, it's about the power to anticipate.
But to make those predictions with any confidence, you need a solid grounding in statistics.
Absolutely indispensable. It's the language you use to quantify uncertainty, identify real patterns versus random noise.
The sources start with the basics. Probability. Understanding likelihood.
Right. Basic probability. The chance of an event happening, like drawing an ace, is 4 out of 52. Simple ratio.
But then it gets more complex with conditional probability, PAB.
Yes. And this is super relevant for machine learning. It's a probability of event A happening, given that event B has already happened.
So it's about updating likelihood based on new info.
Precisely. Imagine predicting if a customer will buy product X. Knowing nothing else, there's some general probability. But if you learn they just bought product Y, and people who buy Y often buy X, that new information, buying Y, changes or conditions the probability of them buying X.
Ah, okay. That's how ML models learn, by seeing how pieces of information relate.
It's fundamental to how they update their beliefs based on the data they see, how one event changes the likelihood of another.
Then the sources mention statistical distributions, patterns in the data.
Yeah, data usually isn't just random chaos. It often follows predictable patterns or shapes. Understanding these helps us model it better.
And the most important one is the normal distribution, the bell curve.
The classic, symmetric, bell-shaped, mean, median, mode, all in the center, described by its mean, average, and standard deviation spread.
Why is it so important?
Well, lots of natural things follow it, approximately. And critically, many statistical tests and ML models assume data or errors are normally distributed. Plus, the empirical rule, 68, 95, 99.7, gives you a quick handle on data spread if it's normal.
Like 68% of data is within one standard deviation of the mean.
Roughly, yeah. Helps understand spread and spot outliers. It's a cornerstone for making inferences from data.
Which leads into hypothesis testing, making decisions based on data.
It's a formal framework for checking a claim. You have an idea about a population, you collect sample data, and hypothesis testing helps you decide if the evidence supports your idea or if it could just be random chance.
You start with the null hypothesis, $, state, the no effect idea.
Right, the default assumption. Like a new website design has no effect on conversion rate. Any difference we see in a small test is just luck.
And the alternative hypothesis is what you're trying to prove.
Yeah, the new design does increase conversion rate. You collect data, calculate a test statistic, how far your sample is from the null expectation, and get a p-value.
The p-value, that's the key, right? Probability of seeing the data if the null was true.
Exactly. Small p-value, say less than 0.05, means your data looks pretty weird if the null hypothesis is true. So you reject the null and favor the alternative.
Like the university ACT score example. Claim is 30, null. Sample average is 28.3. Is that difference statistically significant or just chance?
Hypothesis testing gives you the tools to answer that rigorously. It's the basis for A/B testing websites, testing new drugs, all sorts of things where you need to make a decision based on limited data.
For Alex, getting these stats concepts, that was a big aha moment.
Huge. Seeing how combining domain, knowledge, data, and these statistical tools lets you make educated, quantifiable predictions, it was the essential bridge, getting him ready to actually build machine learning models.
Okay, chapter 4, Building the Future. Alex masters machine learning, ML. This feels like the next big evolution.
It really is. Teaching computers to learn directly from data without explicit programming for every single scenario.
So ML is a branch of AI, using algorithms that learn from data.
Yep. They analyze data, spot patterns, and then make decisions or predictions, getting better as they see more data. The key is they aren't explicitly told how to make the prediction. They learn the how from the examples.
How does it relate to data science overall?
Data science is the broad field of extracting knowledge. ML is a powerful set of tools within data science, specifically for building models that learn and predict. Like the analogy, DS is the rectangle, ML is a square inside it.
And this learning ability, that's what enabled the shift from just descriptive diagnostic to prescriptive analytics.
Absolutely. ML automates and enhances the prediction part. It propelled data science forward.
The sources mention main categories: supervised learning.
That's learning from labeled data. You give the model inputs and the correct outputs. Goal. Learn the mapping so it can predict outputs for new inputs.
And within that, regression for predicting numbers.
Like house prices.
And classification for predicting categories.
Like spam or not spam. Exactly.
The other main type is unsupervised learning.
Right. Learning from unlabeled data. No right answers provided. The goal is for the algorithm to find hidden structures or patterns on its own.
Like clustering, grouping similar things together.
Customer segmentation is a classic example. Finding natural groups in your customer base without predefining them.
And dimensionality reduction, simplifying the data.
Yeah, reducing the number of features while keeping most of the important information can help with visualization or speed up other models.
Now, under the hood, ML runs on math. The sources mention linear algebra.
Yeah, the math of vectors and matrices. It's like the fundamental language for representing data in ML.
A vector is like a single data point.
Yeah.
Age, income, purchases.
Exactly. An ordered list of numbers representing one observation or point in space.
And a matrix is the whole data set. Rows are data points, columns are features.
Often, yes. And linear algebra operations, multiplication, transformation are used constantly inside the models to process this data, find patterns, make predictions. It's how the models see and manipulate the data numerically.
Okay. And calculus comes in for optimization, training the models.
Crucial part. Training often means finding the model parameters, like slope and intercept in a simple line, that minimize the model's error on the training data.
The error is measured by a cost function. Lower cost, it's better model.
Right. And the main algorithm to minimize that cost is often gradient descent.
Okay, how does that work conceptually?
Imagine the cost function is a landscape with hills and valleys. Gradient descent uses calculus, the derivative or gradient, to figure out the steepest downhill direction from your current spot.
Then it takes a step downhill.
Takes a small step in that direction, recalculates the slope, takes another step. It repeats this, iteratively moving downhill, updating the model's parameters each time.
Until it reaches the bottom, the lowest error.
Ideally, yes.
Yeah.
A flat area, the bottom of a valley, that represents the minimum cost, the best parameters found. This iterative process, guided by the gradient, is how many ML models learn. Calculus provides the engine for that learning.
Got it. So with this conceptual understanding, Alex was ready for his advanced workshop, building a simple model with Python and scikit-learn.
Scikit-learn is a fantastic library, makes ML in Python much easier, provides consistent tools for everything.
He started with linear regression, predicting a continuous value.
Yeah, fundamental model. Finding a linear relationship. Predict house price from size or sales from ad spend.
And the workflow followed best practices.
Typically, yes. 1. Import libraries, pandas, numpy, slurn. 2. Load data. 3. Prepare features, X the inputs, and target, Y the output.
4. Split data into training and testing sets. That sounds important.
Critical. You train only on the training set. Then you test on the unseen testing set to get an unbiased idea of how well it generalizes to new data. Common split is 80% train, 20% test.
Okay. 5. Initialize and train the model, like model.fit, xtrain, yitrain.
Yep, that's the learning step. The algorithm finds the best parameters, like the line's slope and intercept, by minimizing errors on the training data, using things like gradient descent internally.
6. Make predictions on the test set.
Predictions model dot predict xtest.
7. Evaluate. Compare predictions to actual test values using metrics like mean squared error, MSE.
Exactly. MSE is common for regression, average squared difference. Lower is better. There are other metrics too, of course.
Building that first model, even a simple one, must have been a big moment.
Huge landmark. Demystifies ML. Shows it's a practical tool you can actually build and use.
And after prediction comes action, prescriptive analytics.
The next logical step goes beyond what might happen to recommending what you should do about it for the best outcome.
So it builds on predictive insights, uses optimization maybe?
Often, yes. If ML predicts high churn risk for a customer, prescriptive analytics might suggest a specific retention offer, considering cost, predicted impact, budget.
Or optimizing delivery routes, considering predicted traffic, weather, costs.
Exactly. It aims for the optimal action. It's really the peak of the analytical journey, turning insights directly into recommended strategies.
Alex then tackled a more real predictive model project, like customer churn or product demand.
Yeah, a more comprehensive process.
Yeah.
Clear problem definition, thorough data collection and prep, often the most work.
And feature engineering, creating new inputs for the model.
Super important, like deriving days since last purchase from transaction dates. Raw dates aren't useful, but that engineered feature can be highly predictive of churn.
Then model selection, choosing the right algorithm, training, and more rigorous evaluation.
Right. Using metrics suitable for the specific problem, like precision and recall for churn, where catching the churners might be more important than overall accuracy.
And the sources say the first model is rarely perfect, so iteration and refinement.
Always. Dealing with overfitting, model too complex, memorizes training data, or underfitting, model too simple, using techniques like cross-validation, tuning hyperparameters, the algorithm settings, trying different algorithms.
And finally, interpretation and action, understanding why it predicts what it does.
Crucial. Which features drive the predictions?
Right.
How can we translate these model insights into actual business actions?
Seeing a model predict and provide actionable insights, that must have been incredibly satisfying.
Immensely. Shows the real power of ML transforming data into foresight and driving concrete actions.
But Alex's journey didn't stop there. The field is huge. Chapter 5 touches on the vanguard, the frontiers like deep learning and NLP.
Right. First, deep learning DL, a specialized subset of ML using artificial neural networks with many layers. That's the deep part.
Inspired by the brain, interconnected neurons.
Loosely inspired, yes. Layers of nodes. Data flows through, forward propagation, calculations happen, weights on connections determine influence.
And it learns through back propagation, adjusting weights based on errors.
Exactly. Calculate the error, send it backward, use optimization like gradient descent to tweak the weights, reducing the error over many iterations.
What makes deep networks so powerful?
Their ability to learn complex hierarchical features automatically from raw data, especially unstructured data like images or text, reduces the need for manual feature engineering.
And they've powered breakthroughs, computer vision, speech recognition.
NLP, autonomous driving. Many cutting-edge AI applications rely on deep learning. Seeing demos can feel like magic.
Another frontier Alex encountered, natural language processing, NLP, making computers understand human language.
That's the goal. Interpret, analyze, understand, even generate language meaningfully, bridging the human-machine communication gap, extracting insights from text and speech.
What are some core NLP tasks?
Tokenization, breaking text into word species. Sentiment analysis, positive, negative, neutral tone. Named entity recognition, NER, finding people, places, orgs in text.
Also things like grammar, part of speech tagging, parsing sentences.
Yep. Understanding the structure and meaning.
And applications are everywhere. Chatbots, translations, spam filters.
Search engines understanding your query intent, social media analysis. It's pervasive.
The challenge is language itself is so complex and ambiguous.
Hugely. Sarcasm, context, cultural references. It's hard. But NLP is crucial for unlocking all that text-speech data.
Exploring DL and NLP showed Alex just how fast this field moves.
Absolutely. It's not static. New tools, algorithms, ethical considerations pop up constantly. AI is even starting to help with data engineering itself.
So that commitment to lifelong learning, it's essential.
Non-negotiable, really. You have to stay curious and adaptable.
Which brings us to the final chapter, chapter 6. Your own adventure, taking Alex's legacy, his journey, and figuring out your path forward.
Let's quickly recap his path from the sources: the awakening, What is data, types, quality? Becoming a data analyst. SQL, BI, Python, Pandas, descriptive diagnostic. Stepping into data science, stats, math foundations, building ML models, predictive, prescriptive, and glimpsing the frontiers, DL, NLP.
And it wasn't just about the tools, but the mindset, right? Curiosity, critical thinking, persistence.
Definitely. A passion for uncovering insights that actually matter.
So Alex's story is meant as inspiration for you, the listener. How do you fuel that ambition?
The sources offer practical advice. First, define your why. What's your motivation, passion, career, solving specific problems? Alex found his in seeing his analysis make a difference.
Second, break down the mountain. Don't get overwhelmed. Learn step by step. Data types, then SQL, then Viz. Build incrementally.
Consistency is key. Little and often beats cramming. 15-30 minutes daily is powerful for retention and avoids burnout.
Find inspiring applications. Connect learning to your interests, climate, health, sports, whatever, makes it relevant.
Create a good study environment. Minimize distractions. Quiet space if possible.
Reward yourself. Celebrate small wins. Finishing a module, building your first model, keeps momentum going.
Join a community. Don't go it alone. Forums, meetups, online groups, support, ideas, networking makes it more fun too.
Use resources that work for you. So many courses, books, tutorials. If one isn't clicking, find another. Match your style and pace.
It's a marathon, yeah. Needs motivation, but also strategy and support.
And the sources really emphasize starting as a data analyst as a great entry point.
Excellent path. Build foundational skills, gain practical experience, deliver value quickly.
Focusing on those core skills. SQL, non-negotiable. Spreadsheets, still vital. BI tools, Power BI, Tableau for communication, and basic Python with pandas.
Yes. Mastering those, plus analytical thinking, lets you tackle tons of real problems. Python is also that bridge if you want to go deeper into data science later.
And remembering that the field is always changing. Continuous learning is key.
Gotta stay curious, stay adaptable.
So Alex's journey shows the path is open if you have the curiosity and persistence.
And understanding data is becoming vital everywhere, every industry.
The power of data, solving problems, driving innovation, making an impact. These skills empower you to contribute.
Your own adventure is waiting. Take that first step. Write one SQL query. Make one chart. Explore one data set.
And as you start using data, remember, the sources suggest the deepest insights often come not just from the numbers,
but from the questions you learn to ask and how you navigate this constantly changing landscape of data itself.
So a final thought to leave you with, what question will you ask first?